On April the 13th, 2029, something the length of 3 football fields will pass closer to Earth than our own satellites. The closest approach of an object, its size, that astronomers have ever seen coming, years in advance. For 2 days in the summer of 2004, a small team of astronomers glimpsed it, then lost it in the dark. Months later, it reappeared, and what they calculated next made headlines around the world. A chance, however small, that this object could strike our planet on this very date. That chance is why its name comes from an ancient god of chaos. What cleared its name, and what 2 space agencies are now racing to do before it ever arrives, is a story most people have never heard. If stories like this one keep you good company at night, consider leaving a quiet like and subscribing. It costs nothing and greatly helps this channel more than you know. Now settle back, close your eyes if you like. In 3, 2, 1, liftoff. On the night of June the 19th, 2004, the sky above southern Arizona was doing what it does on most clear summer nights, holding still so that a handful of people willing to stay awake, for it could look a little further into the dark than anyone had looked the night before. Atop Kitt Peak, in the Quinlan Mountains southwest of Tucson, the dome of the Bok telescope stood open to the air, its 90-inch mirror gathering starlight the way a cupped hand gathers rain. Kitt Peak was not, and is not, a single observatory so much as a small community of them. More than 20 telescope domes strung along one high desert ridge, each belonging to a different institution, each usually aimed at a different target on any given night, the whole mountain humming along on its own overlapping schedule of unrelated research. Nothing about the evening announced itself as historic. There was no siren, no bulletin, no sense inside that dome that anyone present was about to have a hand in one of the more unusual astronomical stories of the new century. There rarely is. The most consequential discoveries in this particular field tend to arrive quietly, tucked inside ordinary work, and this one was no exception. The person most responsible for that ordinary work was a soft-spoken instrumentation engineer named Roy Tucker. Tucker was born in December of 1951 in Jackson, Mississippi, and grew up in Memphis, Tennessee, where a boyhood fascination with radios and telescopes never really left him. By 2004, he had spent years as a senior engineer at the University of Arizona and as an instrumentalist at Kitt Peak itself, but the achievement he seemed proudest of had nothing to do with either job title. In the mid-1990s, on his own property outside Tucson, he had built a private observatory by hand, mixing and pouring the concrete piers himself, and named the place the Goodricke Pigott Observatory, after 2 18th-century astronomers remembered for their pioneering work on variable stars. Working largely alone, on equipment he often designed and built himself, Tucker would go on to discover more than 700 numbered asteroids over the following years, along with 2 comets, a body of work that made him, by any reasonable measure, one of the most prolific asteroid hunters of his generation. He kept chickens. He held a ham radio license. He could recite whole passages of dialogue from his favorite old science fiction films. None of that would matter to the wider world in quite the way this one June night eventually would. Tucker died in Tucson in March of 2021 at 69 years old, having spent a quarter of a century turning a homemade backyard telescope into one of the more productive asteroid hunting operations ever run by a single person. Beside him that night, at least in partnership, if not always in the same room, were 2 collaborators from the University of Hawaii's Institute for Astronomy, David Tholen, born in 1955, and Fabrizio Bernardi, an Italian astronomer working alongside him on the same survey. Tholen was no newcomer to any part of this story. His own doctoral research, completed at the University of Arizona in 1984, produced a system for sorting asteroids into families based on how they reflect light, a classification scheme that still carries his name today and that astronomers continue to rely on. Decades later, whenever they need a first, rough sense of what a given asteroid is actually made of. 7 years after that, in 1991, NASA asked him to sit on 2 advisory committees built around a question that would come to define much of the rest of his career. How, exactly, does a civilization go about finding an asteroid that might strike its own planet, and what, if anything, could be done about it once one was found? By the time he arrived at Kitt Peak in June of 2004, David Tholen was not simply an astronomer who happened to be present. He was one of a small number of people in the world who had already spent years thinking, in a formal, professional capacity, about exactly the kind of object that was about to drift into his camera's field of view. The 3 of them had not gathered at Kitt Peak that night to make history. They were following up on an entirely different, already catalogued asteroid, using the Bock telescope's wide-field camera to pin its position down more precisely, the unglamorous, essential bookkeeping that makes up the bulk of this kind of astronomy. It is worth pausing on that fact because it says something true about how discoveries like this one tend to happen. Nobody was hunting for what they found. They were doing careful, routine, forgettable work, the kind that rarely makes the news, and something else wandered into the frame while their attention was pointed elsewhere. A telescope like the Bock does not notice a moving object the way a person glancing up at a clear sky might. It takes a sequence of images of the same patch of sky, spaced minutes apart, and a computer compares them frame against frame, hunting for anything that shifts position while the stars around it hold still. This technique has a long history in astronomy, older than the computers now used to automate it. In the 1930s, a young observatory assistant named Clyde Tombaugh discovered the planet Pluto using a mechanical device called a blink comparator, which flickered 2 photographic plates of the same star field back and forth in rapid succession, so that anything which had moved between exposures seemed to jump against a background of otherwise motionless stars. The principle Tucker, Tholen, and Bernardi relied on 70 years later was, at its heart, the very same one, simply carried out by software instead of a hand-cranked machine. By 2004, the Bock telescope carried a wide-field camera built around a mosaic of electronic light detectors, distant cousins of the sensor inside any ordinary camera, only larger, more sensitive, and cooled to keep electronic noise from drowning out the faintest signals. Where Tombaugh had compared photographic plates by eye, blinking one against another until his own attention began to flag, a computer now did the blinking, sorting through far more sky, far more quickly than any one person ever could. Stars, for all practical purposes, do not move on a human timescale. Asteroids, comets, and the occasional stray artificial satellite do. That shift, tiny as it looks on a screen, is the entire signature of a nearby solar system object announcing itself. On the night of June the 19th, buried among the frames Tucker, Tholen, and Bernardi had taken while chasing their intended target, something else was doing exactly that, sliding frame to frame in a way that did not belong to any object already known to occupy that stretch of sky. It would have been easy to wave off. Sky surveys of this kind turn up unexpected movers all the time, the overwhelming majority of them perfectly ordinary asteroids, logged within a few days and never thought about again by anyone outside a small circle of specialists. But this one earned a second look, and then a third, because that is simply how the work gets done. Every candidate is checked, whether or not anyone expects it to matter later. The three astronomers observed it again the following night, June the 20th, confirming that the motion was genuine and not some artifact of the equipment, the atmosphere, or a tired pair of eyes at the end of a long shift. 2 nights of data, a rough sense of where the object was and how quickly it was moving. Nothing more than that. Yet, no name, no orbit anyone could fully trust. No way of knowing whether this was one of the thousands of unremarkable rocks that quietly share our corner of the solar system, or something that would need to be watched far more closely. Within days, the discovery was reported to the Minor Planet Center, the clearinghouse headquartered in Massachusetts that keeps the official, running ledger of every asteroid and comet ever found. Every new object receives what is called a provisional designation, built out of the date of its discovery, a kind of temporary name, more filing code than title, meant to hold the object's place in the record until enough is known about its orbit to give it something more permanent. This one became 2004 MN4, the year of its discovery, followed by 2 letters marking roughly when within that year it turned up, followed by a further letter and number distinguishing it from every other object found in that same short window. It is not a name built for poetry. It is a name built for bookkeeping. On the night it was assigned, that is all, this object was one entry in a very long list, among thousands of similar entries added to that same list in that same single year. The accumulated output of survey telescopes working night after night across several continents. Nearly all of those entries were destined to remain exactly what they were on the day they were logged. A date, 2 letters, and a number filed and essentially forgotten by everyone except the handful of specialists whose job it was to keep track of such things. There was, at that point, no reason for anyone outside a small circle of specialists to have heard of it, and no reason to expect that would ever change. The solar system is extraordinarily well stocked with objects like this one, rubble and remnants left over from the earliest days of planet formation, orbiting the sun in numbers that run into the millions, once every fragment down to boulder size is counted. The overwhelming majority never come anywhere near Earth, and most of the ones that do pass by at distances so vast they register as nothing more than a line of numbers in a database, never once glimpsed by a human eye. 2004 MN4 looked, on the strength of its first 2 nights of data, like it might belong to that second, closer category, an asteroid whose orbit brought it near enough to Earth's own path to be worth tracking. But 2 nights of observation is a thin thread to hang any real understanding on, and thin threads, in this line of work, have a habit of snapping before anyone can follow them very far. To understand why 3 astronomers would treat a faint, unremarkable moving point of light with any real urgency at all, it helps to understand the larger project they were quietly a part of. Earth orbits the Sun inside what amounts to an enormous debris field, the leftover construction material of the solar system's own formation some 4.5 billion years ago. Most of that material has stayed roughly where it has always been, out among the asteroid belt between Mars and Jupiter, or farther still, in the cold outer reaches beyond Neptune. But a meaningful fraction of it, tens of thousands of known objects, and very likely many more not yet found, follows orbits that cross or come close to Earth's own path around the Sun. Astronomers call these near-Earth objects, and watching for them is not a hobby and not simple curiosity. It is, formally, a mandate handed down by the United States government, and that mandate had a specific, vivid origin. A decade before this particular night at Kitt Peak, in July of 1994, a broken comet called Shoemaker-Levy 9 slammed into the planet Jupiter across 6 extraordinary days. Its fragments, some more than half a mile wide, striking the planet one after another, while telescopes across the world, and eventually the Hubble Space Telescope itself, watched it happen in something close to real time. It was the first collision between two bodies of the solar system that human beings had ever directly observed, and the scars it left behind in Jupiter's clouds, some larger than Earth itself, remained visible through modest backyard telescopes for months afterward. The impact never threatened Earth directly. Jupiter was the target, not us. But it did something almost as important. It turned an abstract danger into something suddenly, vividly concrete. If a comet could tear open the largest planet in the solar system like that, the same laws of physics applied, without exception, to smaller, rockier worlds like our own. Within a few years, Congress had acted. In 1998, lawmakers directed NASA to find and catalogue 90% of the near-Earth objects at least 1 kilometer across. Objects large enough that a direct impact would be a global catastrophe, capable of throwing enough debris into the atmosphere to darken skies and disrupt climate on every continent at once, in roughly the same size range associated with the object thought to have ended the age of the dinosaurs. That effort became known, informally, as the SpaceGuard goal, and it was carried out not by any single grand observatory, but by a loose network of comparatively modest telescopes scattered across the American Southwest and beyond. Survey programs with names like Spacewatch, Linear, the Lowell Observatory Near-Earth Object Search, and the Catalina Sky Survey, each one quietly scanning its assigned patch of sky, clear night after clear night, for exactly this kind of faint, moving intruder. Alongside those large automated efforts sat smaller, more improvised observing runs, exactly like the one Tucker, Tholen, and Bernardi were carrying out that June astronomers who might spend one night chasing a wide, automated surveys leftover targets, and the next night testing new equipment or refining the orbit of something a bigger program had only glimpsed in passing. The whole system depended on both halves working together. Broad automated nets to catch as much as possible, and smaller, more careful hands to follow up on whatever those nets happened to snag. By around 2009, roughly a decade after the mandate began, that scattered network had accounted for the overwhelming majority of that largest, most dangerous size class. It was, by most reasonable measures, a quiet success story, a real, funded, sustained effort to know what large objects share our neighborhood of the solar system, carried out for years before most people ever had reason to think about it at all. But a kilometer-wide object is not the only size worth worrying about, and the people running these surveys knew it even in 2004. Objects considerably smaller than that a few hundred meters across, large enough to devastate a region without threatening the planet as a whole, are both more numerous and, in a very real sense, more dangerous to any single community unlucky enough to be underneath one, precisely because there are so many more of them still left to find. Within about a year and a half of this particular night at Kitt Peak, Congress would expand NASA's mandate again, directing the agency to find 90% of near-Earth objects 140 meters across, or larger, roughly the size at which an impact stops being a curiosity for astronomers and starts being capable of leveling a city or scarring a landscape for a very long time. That expanded goal would prove far harder to reach than the first one had been. Smaller objects are fainter, more numerous, and considerably easier to miss, and even many years later, the search for them would remain a long way from finished. Within 9 years of this particular night, in a Russian city called Chelyabinsk, the world would receive an unplanned demonstration of what even a modest object can do. A rock roughly 20 meters across, small enough and approaching low out of the morning sun's own glare, that no telescope on Earth saw it coming, entered the atmosphere at a shallow angle and exploded above the city with a force that shattered windows for miles around, injuring more than 1,000 people, almost entirely from flying glass rather than the blast itself. It is worth remembering that detail about the sun's glare. It will matter again later in this account in a much smaller and far less dramatic way. 20 meters is small. It is a small fraction of the 140-meter threshold Congress had set as a bare minimum concern, and smaller still than the object now sitting, half understood, in the data at Kitt Peak that June. Nobody in that dome in 2004 could have known Chelyabinsk was coming. It would not happen for nearly a decade. But the same instinct that sent Tucker, Tholen, and Bernardi back to their telescope for a second and third look at an unremarkable moving point of light was the instinct that, years later, would make Chelyabinsk feel less like a freak accident and more like a preview of something that had always been true. Somewhere out there, unnoticed, are objects large enough to matter and small enough to hide. Finding them before they find you is not paranoia. It is simply better than the alternative, which is finding out the hard way with no warning at all. This is the world 2004 MN4 had quietly wandered into, a solar system under deliberate, chronically underfunded surveillance, watched by a small number of telescopes and an even smaller number of dedicated people, most of them working long, cold nights for reasons that had very little to do with recognition. Roy Tucker was one of those people. So, in his own way, was David Tholen, who by 2004 had already spent a long stretch of his career on exactly this kind of search, and so was Fabrizio Bernardi, working quietly alongside them both. What the three of them had found on June the 19th might turn out to be nothing more than one more addition to a very long list, or it might not. From 2 nights of data, there was simply no way yet to know which. 2 nights of observation can tell an astronomer a great deal, and also, in an important sense, surprisingly little. From that short a baseline, it is possible to sketch a rough orbit, a first approximation of the path an object takes around the sun, built from the tiny amount its position shifts against the fixed background of stars. But a rough orbit is exactly that, rough. The uncertainty in a 2-night orbit is enormous by the standards of celestial mechanics, less a single confident line than a wide, blurry band of possible paths, any one of which might turn out to be closer to the truth than the others. It is not unlike the old problem faced by a ship's navigator working only by dead reckoning, with no landmarks and no fixed stars yet confirmed. A compass, heading, and a rough speed can place a vessel somewhere on the ocean, but not precisely where, and the smallest early error only grows larger the further the ship sails before anyone checks the math again. An object can look, from 2 nights of data alone, like it swings uncomfortably close to Earth at some point decades in the future, when the true orbit, once properly refined, passes nowhere near it at all. The reverse can be true just as easily. With only 2 nights of observation behind it, there was simply no way for anyone to know which story 2004 MN4 was actually going to tell. To place that uncertainty in more concrete terms, a 2-night orbit might let an astronomer say, with real confidence, roughly which planets an object's path crosses, and roughly how long it takes to circle the sun once. It says almost nothing reliable about exactly where that object will be on a particular afternoon 2.5 decades from now. And for an object whose orbit brings it anywhere near Earth's own, that particular afternoon is precisely the detail that eventually matters most. The only real cure for that kind of uncertainty is more data, more nights, spread across more weeks, and, ideally, more years. So an object's true path can be resolved with steadily increasing confidence, the way a photograph slowly sharpens out of grain and static as more and more light is allowed to fall on the same frame. Astronomers call this follow-up observation, and in its own quiet way, it matters more than the discovery itself. A discovery only tells you that something is out there. Follow-up is what eventually tells you what it actually is, and where it is actually going, and whether it belongs on a list anyone needs to worry about at all. Without it, an object like 2004 MN4 is little more than a rumor with a filing number attached to it. Real, certainly, logged and accounted for, but not yet understood in any way that matters. That is precisely the work Tucker, Tholen, and Bernardi set out to do in the days that followed their second night of observations. It should, by rights, have been straightforward. It was not. There is a particular kind of patience this work demands, one that has very little to do with the popular image of a scientist racing against a ticking clock. Most nights spent chasing an object like this, one end in nothing more dramatic than a logbook entry and a plan to try again whenever the schedule and the sky next cooperate. Tucker, dividing his time between Kitt Peak and his own smaller telescopes back in Tucson, understood that rhythm better than almost anyone. It was the same unhurried, repetitive rhythm that had already produced hundreds of his other discoveries, one unremarkable observing run at a time, long before this particular object ever crossed his frame. Astronomical telescopes, even large, well-equipped ones like the Bock, are booked constantly, their nights parceled out months in advance to researchers pursuing dozens of unrelated projects that have nothing to do with any particular newly discovered asteroid. The three astronomers did not have the luxury of simply returning to the instrument whenever they wished. Their scheduled time on it was limited, and once it passed, chasing down 2004 MN4 meant either waiting for the next available opening or persuading somebody else's carefully planned night to make room for a few extra minutes pointed at an unremarkable patch of sky. That kind of negotiation takes time, and time turned out to be exactly what this particular object was not going to give them. Weather added its own complications, as it tends to in this line of work, no matter how well an observing run is planned. Clear nights over southern Arizona in June are common, but never guaranteed, and even a single stretch of cloud is enough to break the chain of consecutive observations. An astronomer needs to keep steadily tightening an orbit. Worse still, for anyone trying to track a faint, newly discovered object, was the moon. A bright moon does not blind a telescope outright, but it does wash out the surrounding sky, raising the background brightness enough that faint, fast-moving objects can slip below the threshold of what even a sensitive camera can reliably pick out from the noise. For several nights that June, the moon itself effectively stood between three astronomers and the object they were trying to pin down, a bright and entirely blameless obstacle that no amount of persistence could argue with. By the time the sky finally cleared and the moon had moved out of the way, a different problem had quietly taken its place, and this one had no simple fix at all. The orbit of 2004 MN4 was carrying it, from Earth's point of view, closer and closer to the direction of the Sun itself, a slow drift astronomers describe as a shrinking solar elongation. An object that lies near the sun in the sky is only observable for a narrow window around dawn or dusk, low against the horizon, through the thickest and most turbulent slice of the atmosphere, before it disappears entirely into daylight for weeks or months at a stretch. That is precisely what happened here. The very orbital motion that had carried this object briefly into view in the middle of June was now carrying it back out of view into the sun's glare on a schedule nobody, at Kit Peak, controlled, and nobody could talk their way around. The result was almost anticlimactic. There was no dramatic error to point to afterward, no equipment failure, no single moment where anyone could say the discovery had been lost through carelessness or a mistake anybody made. It simply ran out of runway, a scheduling conflict here, a few cloudy nights there, an inconveniently bright moon, and then, finally, a sun that would not get out of the way until the object that had briefly announced itself in the data on June the 19th slipped back into the ordinary invisibility that swallows the overwhelming majority of everything the night sky quietly contains. In everyday language, losing something usually implies carelessness, an object slipping out of a pocket or off a shelf through simple inattention. In this branch of astronomy, losing an object means something closer to the opposite. It means the geometry of an enormous, indifferent solar system has, for entirely mechanical reasons having nothing to do with anyone's diligence, carried something briefly visible back into the vastly larger portion of the sky and the calendar where almost nothing is visible at all. It happens constantly. Objects are found, glimpsed for a handful of nights, and lost again all the time, sometimes rediscovered years later, and quietly matched back up to an old, half-remembered designation, more often never seen again at all. There was, in the summer of 2004, no particular reason to think 2004, MN4, would turn out to be any different. For the rest of that summer, and on into the autumn, 2004 MN4 existed only as an entry in the Minor Planet Center's steadily growing catalogue, a string of characters, a rough and still uncertain orbit, and a handful of measurements taken over 2 brief nights before the sky and the calendar quietly closed the window on any more. Somewhere inside that thin, incomplete data, though nobody could have known it yet, was the outline of an orbit that would eventually bring this particular object back into view of Earth in a way almost nothing its size ever had before. But an outline is not a picture. In the late summer of 2004, nobody involved had anything more than the outline, and no way yet to know what it actually described. Roy Tucker went back to his own backyard observatory in Tucson, and to the long, patient work of finding more of the hundreds of asteroids that would eventually carry his name into the discovery record. David Tholen went back to the broader search that had already occupied so much of his career, one faint moving object among the many he tracked in any given year. Fabrizio Bernardi went back to the same quiet, unglamorous survey work all 3 of them had been doing before. This particular object briefly interrupted it. For most objects picked up and then lost this way, that is precisely where the story ends, filed, forgotten, occasionally rediscovered by chance years afterward, and matched back up to an old, half-remembered string of letters and numbers, more often never seen again at all. There was nothing in the evidence available that summer to suggest 2004 MN4 would be any exception to that pattern. It is worth sitting with that for a moment. An object that would eventually carry a name known to millions, tied to one of the more carefully documented close encounters in the modern history of astronomy, spent its first several months of existence as nothing more than an entry nobody thought twice about. Most of what eventually becomes remarkable starts out looking exactly like everything around it. There was nothing yet in the late summer of 2004 to suggest this particular string of letters and numbers was any different from the thousands of others quietly filling the same ledger. It was, whatever this object actually was, however large, however far away, however close its true path might eventually carry it to Earth someday, none of that was yet knowable. From 2 nights of data collected in the middle of a June that, at the time, felt like any other, the answer was still out there, folded into an orbit nobody had finished solving, waiting for someone to pick up the thread again. Later that same year, somebody would, and when they did, the unremarkable filing cabinet entry called 2004 MN4 would not stay unremarkable for very long. 6 months passed before anyone picked the thread back up, and when it happened almost by accident, the same way the whole story had started in the first place. Kitt Peak had long since moved on to other targets. The observing runs that June had produced had been folded into the ordinary churn of the survey work, filed and mostly forgotten, exactly as expected. Nothing about the last week of that particular year gave any early warning that it would turn out differently. On the 18th of December, 2004, half a world away from Kitt Peak, an astronomer named Gordon Garrard was working the night sky over Siding Spring Observatory in the Warrumbungle Mountains of New South Wales, Australia, using a wide-field instrument called the Uppsala Southern Schmidt Telescope as part of a survey program built for exactly this purpose, sweeping the southern sky for near-Earth objects that observatories in the Northern Hemisphere could never see. Garrard was, in his own way, cut from the same cloth as Roy Tucker back in Arizona, an astronomer with a long, quiet record of finding things nobody had sent him out looking for in particular, content to let the sky decide what the night's discovery would be. He had already been credited with finding other asteroids of his own, and in the years ahead he would go on to discover comets bright enough to be tracked by amateur skywatchers around the world, the kind of career built one unremarkable observing session at a time, the same way Tucker's had been. That December night, something in his data caught his attention, a faint, moving point of light, the familiar signature of an asteroid nobody had yet accounted for. It took a few days of careful cross-checking before anyone made the connection. Matching a freshly observed object back to an old, half-forgotten designation is its own small piece of detective work. An astronomer takes the rough, uncertain orbit, computed from the new observations, and asks whether it could plausibly describe the same path as any of the thousands of incomplete, unconfirmed orbits already sitting in the Minor Planet Center's files, waiting for exactly this kind of match. Most of the time, the search comes up empty, and a new object simply stays new. This time, it did not. On the 20th of December, the Minor Planet Center issued the formal bulletin that tied the two observations together. The object Garrard had just picked up over Australia, and the object Tucker, Tholen, and Bernardi had briefly glimpsed and then lost over Arizona 6 months earlier, were one and the same. 2004 MN4 was found again. There is something almost tender about that fact, if you sit with it for a moment. An object drifts through the solar system for 4.5 billion years without a single human being noticing it. Then, within 1 calendar year, it is noticed twice, on opposite sides of the planet, by 2 small teams of astronomers who had no idea the other existed, each one simply doing the same patient, unglamorous work the other had already done months before. The universe did not make this easy. It made it possible and then left the rest to persistence. The reunion was not quite seamless. Once the connection was made, a careful review of the original June measurements turned up small errors in the recorded positions and timing, the kind of minor discrepancy that is almost inevitable when an object is caught for only 2 brief nights and then not looked at again for half a year. David Tholen himself went back through the original data and corrected it, tightening the very first thread of this object's recorded history before anyone could build anything reliable on top of it. It was a small, unglamorous piece of work, the sort that rarely gets mentioned in any retelling of this story, and it mattered anyway, because everything that followed over the next several days depended on getting that early thread exactly right. Persistence, though, was about to run headlong into a very different kind of attention. The moment the December and June observations were formally linked, the object stopped being a curiosity and became a case file. 2 automated systems, one run out of NASA's Jet Propulsion Laboratory in California called Sentry, and a counterpart called NEODIS, jointly operated by researchers at the University of Pisa in Italy and the University of Valladolid in Spain, exist for exactly this purpose. Each night, without being asked, they take every known near-Earth object's best available orbit and run it forward across the coming century, checking whether any plausible version of that orbit brings the object close enough to Earth to be worth a second look. For nearly every object in their catalogue, the answer comes back clean: no concern, nothing to report. On the 20th of December, 2004, for this particular object, the answer did not come back clean. Both systems, working independently of one another, flagged the same unsettling result. Somewhere within the still wide range of orbits consistent with the available data, 6 months of gaps between observations leaves a great deal of room for uncertainty, sat a path that would bring 2004 MN4 back to Earth on the 13th of April, 2029. Close enough to strike it. Astronomers have a specific term for a single such path within that broader cloud of possibilities: a virtual impactor, a mathematically valid solution consistent with everything observed so far, that happens to end in a collision rather than a harmless pass. Finding one virtual impactor inside an otherwise reassuring cloud of possible orbits is not unusual and rarely means much on its own. The true orbit almost always turns out to be one of the many harmless solutions instead, and the virtual impactor quietly disappears as soon as enough new data rules it out. What made this particular case worth watching was not the mere existence of a virtual impactor, but how much of the surrounding cloud of possibility it represented, and how stubbornly it kept surviving each new round of observations rather than being ruled out the way most virtual impactors are within days. Not a certainty, not even, at that point, a likelihood. Just a possibility sitting inside the range of what the data could not yet rule out. But it was there, acknowledged by 2 separate systems on 2 separate continents. And once something like that appears on the board, it does not simply get ignored until somebody proves otherwise. To understand what happened over the following week, it helps to understand the instrument astronomers use to talk about exactly this kind of possibility. The Torino scale, introduced only a few years before this object was found, works something like the color-coded warning systems familiar to anyone who has ever watched a hurricane forecast on the evening news. It runs from 0 to 10. A 0 means an object poses effectively no threat at all, the overwhelming resting state of nearly everything ever tracked. In an ordinary year, dozens of newly found objects might brush up against a level 1 rating for a few days, simply because their orbits are too new to rule anything out completely, only to settle back to 0 as soon as a handful of additional observations arrive. The highest numbers, reserved for certainties involving genuinely massive objects, describe outcomes nobody has ever had to assign in the real world. In between sits a graduated scale that weighs two things at once: how likely an impact currently appears, and how much damage that impact would cause if it happened. A faint, distant possibility involving a harmless-sized object stays near zero. A serious, well-established probability involving something large enough to matter climbs the scale quickly. The number is not a prediction. It is a measure of how urgently a particular object deserves the attention of professional astronomers, updated as new information comes in, and very often it settles back down towards zero within days or weeks as follow-up observations narrow the range of possible orbits. 2 days after the December connection was made, on the 22nd of December, 2004, MN4 reached level 2 on that scale. It was the first object since the scale had been adopted to climb that high. Nobody tracking near-Earth objects for a living had ever had to assign that particular number to anything before. There is a particular kind of attention that gets paid to a genuine first, distinct from the attention paid to something merely unusual, and the small international community of people who did this work for a living paid it. For Roy Tucker and David Tholen in particular, the news carried a strange, doubled weight. This was not simply a story they were reading about. It was an object they themselves had found 6 months earlier, on a night neither of them had any reason to remember as especially significant at the time. Tholen, who had already spent more than a decade thinking professionally about exactly this kind of scenario, understood better than almost anyone what a rising Torino scale number actually meant and did not mean. He also understood, better than almost anyone, how quickly that number tended to fall once enough additional data arrived. Tucker, back at his own small observatory in Tucson, found himself watching the progress of an object he had first noticed as an unexpected blur in someone else's frames, now being discussed in terms usually reserved for genuine planetary emergencies. Neither man, by most accounts, panicked. Both understood the process well enough to know that a young orbit, built from too little data, can look far more alarming than the true picture eventually turns out to be. But understanding a process intellectually and watching it unfold around your own discovery in real time over a holiday week are not quite the same experience. What made the news when word of it eventually reached beyond that small community was not the technical language of orbital uncertainty or virtual impactors or Earth-crossing corridors. What made the news was a single simple number, a chance, however remote, that a large rock might someday strike the planet on a specific date that people could circle on a calendar. Fabrizio Bernardi, the third member of the Discovery team, followed the same climbing numbers from his own vantage point within the broader University of Hawaii survey effort, a quieter presence in most retellings of this story than either of his two better-known colleagues, but no less a part of the reason any of this was being tracked at all. The public, by this point, already had a ready-made framework for a story like that. In the years following the Jupiter comet impact that had helped inspire the SpaceGuard mandate in the first place, Hollywood had released a pair of big-budget disaster films built around exactly this premise, both of them familiar to a wide American audience by 2004. Nobody tracking 2004 M4 in real life was staring down anything resembling a movie plot, and the astronomers involved were quick to say so whenever asked. But the cultural groundwork for how this kind of headline would be received had already been laid years before this particular object was ever found, and newspapers reached for the object's temporary, unglamorous designation and found it wanting. Headlines began referring to it, informally and a little dramatically, as a doomsday asteroid, a label that said far more about how the story would be told than about what the data actually supported, but a label that stuck all the same. Wire service reports carried the story from newsroom to newsroom over the following days. Evening broadcasts gave it a few sentences between the holiday weather and the year-end recap, and for a brief stretch that December, an object that had spent its entire existence as an anonymous string of letters and numbers became, however briefly, a subject of dinner-table conversation in households that had never before had reason to think about near-Earth asteroids at all. It is worth pausing here to make the abstract danger concrete, in the same spirit that led Congress to draw its own size thresholds years earlier. The earliest rough estimates of this object's size, based on nothing more than how much sunlight it reflected, put it in the neighborhood of 450 meters across, an estimate that would later be refined and complicated as more precise measurements came in, but one that, even in its rough form, gave people something to hold on to. 450 meters is close to the full height of the Empire State Building, antenna included, tipped on its side and set loose at several miles a second. It also dwarfs the 20-meter object that would streak over Chelyabinsk years later, more than 20 times the diameter, which on its own translates to many thousands of times the mass, packed into a single tumbling body. An object that size does not need to strike a major city to cause devastation on a scale almost impossible to plan around. Depending on where it came down, the energy released could level a metropolitan area, or send a wall of water across a coastline, or scar a stretch of countryside for a generation. This was never, at any point in this particular story, a planet-ending event of the kind associated with the extinction of the dinosaurs. It was something smaller and, in its own way, more unsettling. A regional catastrophe with a specific, calculable date attached to it, discovered by 3 amateur-minded astronomers testing equipment on an ordinary night in Arizona. And yet, for all that, nothing resembling an emergency was declared anywhere in the world that December, and it is worth understanding exactly why not, rather than assuming the danger was simply being downplayed. A quarter century is an enormous amount of time in this field. Every year that passed between then and 2029 would bring new observations, and every new observation would narrow the range of possible orbits a little further, the same process that had already carried this object from an unremarkable filing entry to a record-setting risk figure in a matter of days. Astronomers responsible for public communication understood, even in the thick of that climbing number, that the overwhelming historical pattern for objects like this one was resolution, not confirmation small, early risk figures being whittled down to nothing as better data arrived again and again in case after case that had come before. That pattern was not yet a promise. On the 27th of December 2004, nobody could responsibly promise anything at all, but it was a reason to keep working calmly rather than to sound an alarm nobody yet had grounds to sound. It did not yet have the name most people would eventually come to know it by. That name was still 7 months away, and when it finally arrived, it would arrive for reasons that had everything to do with the week this story is now describing. Minor planets earn their permanent names only after their orbits are understood well enough to be trusted. Abar 2004, MN4, would not clear until the following June. Once it did, its discoverers were given the traditional right to propose a name, and the one they settled on, the following July, was Apophis, the Greek rendering of Apep, the ancient Egyptian god of chaos and darkness. In the mythology the name comes from, Apep was imagined as a vast serpent coiled in the eternal dark of the underworld, waiting each night to swallow the sun god Ra whole as he made his passage beneath the world before sunrise. Only the intervention of another god, Set, guardian of storms in the desert, was said to hold the serpent back night after night so that the sun could rise again each morning. It is, at its heart, a story about a nightly, uncertain struggle to make sure the sun keeps coming back, which is either a striking coincidence or a very fitting piece of ancient imagery to attach to an object whose entire story, that December, revolved around whether it would someday come back to meet the Earth. On its surface, the choice reads like exactly the kind of theatrical flourish a newspaper headline would have appreciated. In practice, it followed a naming convention astronomers had used for years, largely unrelated to any newspaper at all. Asteroids, belonging to the orbital family. This object currently occupied are traditionally given Egyptian names. Asteroids, belonging to a different orbital family, the one this object's 2029 encounter with Earth's gravity would eventually push it into, are traditionally given Greek names instead. Apophis, a Greek name for an Egyptian god, was less an omen than a small, deliberate joke about orbital mechanics, chosen by people who understood exactly what this asteroid's own future held. There was a second joke folded into the first one, smaller and more personal, which David Tholen would later confirm himself when asked about it directly. He and Roy Tucker were, it turned out, both fans of a science fiction television series in which a recurring villain drawn from the same Egyptian mythology carried the same name. Tholen called it a happy coincidence rather than a deliberate homage, and there is no reason to doubt him. But it is a fitting detail, all the same, a reminder that the people doing this work were not remote, humorless technicians. They were people with favorite television shows and homemade observatories and chickens in the backyard, doing careful, exacting science and still finding room, when the moment allowed it, for a small private joke about a monster from television, sharing a name with a very real object in the sky. None of that softened what was happening in the data that same week. If anything, the days immediately following the 22nd of December made the picture worse, not better. This is one of the counterintuitive truths of orbit determination that rarely makes it into the popular imagination. Gathering more data does not always make a risk assessment more reassuring right away. Sometimes it does the opposite, at least for a while. Imagine a wide net thrown out to catch every possible version of an object's true path, virtually all of them harmless, and a small handful of them landing distressingly close to Earth. Early on, with very little data, the net is enormous and loosely woven, and the dangerous strands are only a small fraction of everything inside it. As more observations arrive, the net tightens. Most of the time, tightening the net simply throws out more of the harmless possibilities and the alarming ones along with them, and the overall risk estimate drops. But every so often, purely by the mathematics of it, tightening the net concentrates the remaining possibilities rather than eliminating them, and the risk estimate climbs instead. Picture that same net being drawn steadily smaller around a single patch of open water, right up until the moment it closes on nothing at all. Drawing it tighter can make whatever remains inside look more crowded, not less, even though the total number of fish, so to speak, has done nothing but shrink the entire time. That is precisely what happened to 2004 MN4 in the final days of December. Each new round of observations should, by instinct, have made things feel safer. Instead, for one restless week, they made things feel worse. The days between the 22nd and Christmas itself were not quiet. Fresh astrometry kept arriving from whichever observatories around the world happened to have both clear skies and a free moment to spare, on an object most of them had never heard of. A week earlier, a night's data from one, continent folded into the calculation before the next continent's night had even begun. The entire, informal, worldwide relay, running on nothing more than professional habit and a shared understanding that this particular case deserved the extra effort. Astronomers who might otherwise have taken the holiday off found themselves checking updated orbital solutions between family gatherings, watching a number that, by every professional instinct they had, should have been trending towards zero and was instead trending the other way. The team running the NEODIS system in Italy would later describe those particular holidays as something close to chaos in their own right, an unplanned professional emergency, arriving at the exact moment most of the world had set work aside. Every new batch of observations, gathered by whichever telescopes around the world happened to have clear skies and available time that night, had to be folded into the calculation almost as soon as it came in. The orbital solution recomputed, the resulting probability checked against the day before, and the whole small international circle of people responsible for the answer kept quietly, continuously informed of where things currently stood. There is a particular loneliness to that kind of work, knowing something the rest of the world does not yet know, watching a number climb on a screen while everyone else is home for the holidays, with no way yet to say whether the story would end quietly or not. On the 24th of December, 2004, Christmas Eve 2004, MN4 reached level 4 on that same scale, a rating meaning, in the plain language the scale itself uses, a close encounter meriting genuine concern, one serious enough to justify an official public statement from the astronomical community. And there it stayed, through Christmas Day itself, through the day after, all the way to the 27th of December, 4 straight days at a rating no object had ever reached before, and none has reached since. On that final day, the 27th, different tracking centers, running their own independent calculations, converged on the highest specific figures the case would ever produce, a chance of impact on the 13th of April, 2029, that different systems placed at somewhere around 2 7/10%, or very roughly 1 chance in 37. However the exact decimal was expressed, the meaning was the same. Out of every measure astronomers had ever assigned to an object crossing anywhere near Earth's orbit, none had ever reached this high, before or since. That agreement between separate systems mattered more than the number itself. Sentry, in California, and NEODIS, split between Italy and Spain, were built by different teams, running different software, checking each other's work without either one depending on the other. When 2 independent calculations, built from scratch by people who had never coordinated their methods, arrive at nearly the same alarming answer, that is not a glitch to be explained away. It is confirmation. Whatever this number represented, it represented something real in the data itself, not an error introduced by any single observatory, telescope, or tired analyst working too close to a holiday. In a real sense, this was the first genuine test of everything the SpaceGuard effort had been built to do. The whole apparatus, the scattered network of survey telescopes, the automated risk calculation systems built and cross-checked by teams who had never needed to lean on each other quite this hard before. The International Clearinghouse in Massachusetts, quietly matching designations against one another, existed for exactly this scenario, and until the last week of December 2004, it had never actually been asked to perform under real pressure. The Torino scale itself was barely a few years old. Nobody involved had lived through a genuine level 4 before, because a genuine level 4 had never happened before. In that sense, whatever this particular week turned out to mean for the planet, It already meant something for the small community that had spent years quietly building the tools to watch for exactly this kind of situation. The tools worked. They caught something, whether what they caught would ultimately prove dangerous or not. The surveillance itself, patched together from modest telescopes, volunteer hours, and a government mandate written years before anyone knew it would matter this much this soon, had done precisely what it was designed to do. Almost none of this reached most people at all, and the small fraction that did reach them mostly arrived as a passing curiosity rather than a genuine worry. Across the country, and across most of the world, the final week of 2004 looked exactly like any other final week of any other year. Holiday travel, year-end retrospectives on the evening news, quiet houses settling into the ordinary rhythm between Christmas and New Year's Day. Nobody rearranged their plans. Nobody needed to. The gap between what a handful of specialists were watching unfold on their screens and what everyone else was doing that week was not a failure of communication. It was simply the accurate reflection of where things actually stood. A real number, rising for real reasons, describing a possibility a quarter century away that still had every chance of dissolving into nothing the moment enough new information arrived. That gap between quiet public indifference and quiet professional urgency would not last much longer. But on the 27th of December itself, it was still very much intact. What the astronomical community actually said publicly during that stretch is worth noting, because it was not what the doomsday headlines implied. Rather than a single dramatic announcement, the public record for this object during that final week of December reads as a series of measured, carefully worded updates from the Minor Planet Center and the two risk tracking systems themselves, each one stating plainly what the current data did and did not show, each one stopping well short of anything resembling alarm. It was not the language of a crisis being managed. It was the language of professionals doing exactly what they were trained to do, reporting the number, explaining what it meant, and continuing to work the problem. Sit with that number for a moment. The way the people tracking it in real time had no choice but to sit with it. One chance in 37 is not a coin flip. It is not even close to one. But it is not nothing either, and for an object roughly the height of the Empire State Building, on a path that would bring it back to a specific place above a specific stretch of the planet, on a specific afternoon a quarter century away, one chance in 37 was enough to make a serious astronomer's pulse quicken. There was no way, on the 27th of December 2004, to know whether that number was about to keep climbing, hold steady, or begin, at long last, to fall. Nobody tracking it that week had the luxury of already knowing how the story turned out. Somewhere out past Christmas and the last quiet days of the year, an answer existed. It simply had not been found yet, and there was no way to know from inside that week whether it would arrive in days, in months, or not at all before the number climbed higher still. Newspapers would move on to other stories within days, the way newspapers always do. The holiday would end. Most of the households that had spent a few minutes over dinner discussing a distant, oddly named threat would rarely think about it again, one way or the other, unless the story happened to resurface. But for the small circle of people who had spent that particular Christmas week watching a number climb on a screen, Tucker in Tucson, Tholen and Bernardi in Hawaii, Garrad in Australia, the teams running Sentry and Neodize, an ocean apart from each other, there was no such luxury of moving on. They simply had a number, a record nobody had ever set before and nobody has matched since, and a growing sense that somewhere in all the work still ahead of them was the answer that would finally settle it, one way or the other. Nobody watching that number on the 27th of December had any way of knowing how soon that answer was coming or how it would arrive. Here is the detail that makes the 27th of December almost unbearable to sit with. Once you know it, at the very hour, the risk figure reached its highest point anywhere in the world. The answer that would end the whole crisis already existed. It was not hiding in some distant archive, on some other continent, behind some barrier of language or bureaucracy that might excuse the delay. It was sitting in a set of images taken at Kitt Peak, the same mountain in Arizona where Roy Tucker, David Tholen, and Fabrizio Bernardi had made their original discovery 6 months earlier, gathered by an entirely different survey team who had no idea what they were sitting on. Nobody had looked at those particular frames yet. In the context of an asteroid nobody had known to search for when the images were taken. That was about to change. On the very same day, the number reached its worst. The Spacewatch survey, based at the University of Arizona and operating its own telescope on Kitt Peak, keeps an enormous running archive of every patch of sky it has ever photographed, most of it never examined closely, unless some later reason gives astronomers cause to go back and look. That archive existed for reasons that had nothing to do with Apophis specifically. Spacewatch had been quietly logging the sky over Kitt Peak for years, one routine night at a time, long before this particular object ever crossed anyone's field of view. On the 27th of December, with Apophis holding at the highest rating any object had ever reached, a small team working the case, among them Spacewatch astronomers Anne Descour and Ariana Gleason, went looking through that archive for exactly this kind of reason. The search itself was tedious, careful work, taking the best available orbit for Apophis, however uncertain it still was, and calculating backward to ask where in the sky the object would have appeared on any given earlier date, then checking whether Spacewatch happened to have pointed a telescope at that particular patch of sky on that particular night. Most such searches come up empty. This one did not. If Apophis had passed within range of any Kitt Peak telescope before its official discovery in June, the frames would already be sitting there, waiting, taken by people who had no reason at the time to know they were photographing anything unusual at all. The search paid off. Buried in images taken on the 15th of March, 2004, 3 months before Tucker, Tholen, and Bernardi ever noticed the object at all, was Apophis, caught quietly in the frame, its position recorded by a telescope that had simply been surveying its assigned patch of sky that particular night. Those March images did something no amount of December data could do on its own. They extended the observed arc of Apophis's path backward by 96 days, roughly tripling the total stretch of time across which its position was known. An orbit calculated from a longer arc is a fundamentally more trustworthy thing than one calculated from a short one. In the same way, a sentence becomes easier to complete correctly the more of it you have already read. 96 days does not sound like a large number next to the 4.5 billion years of this object's existence, but for the specific purpose of pinning down an orbit, those particular 3 months mattered more than almost any other stretch of time in Apophis's entire recorded history. The Minor Planet Center issued the new data that same day, and the team running the NEO-DICE system in Italy, the same team that had spent the previous week watching the risk figure climb immediately, began a fresh calculation built around the newly lengthened arc. That run started at 11 o'clock that night, Central European Time. It finished at 1:37 in the morning on the 28th of December. The result was almost anticlimactic. After everything that had led up to it, the 2029 impact possibility had vanished, not reduced, not downgraded, gone, cleanly, the way static disappears the instant a radio dial finally lands on the station, rather than fading out gradually as it gets closer. Within roughly 11 hours of Apophis reaching a record that no object had ever reached before, the specific danger behind that record had been eliminated by a set of photographs nobody had thought to check 3 months earlier. The crisis that had occupied a small, worldwide community of astronomers through an entire holiday week was over before most of the households that had briefly discussed it over Christmas dinner even knew there had been a resolution to look for. Measured from the moment 2004, MN4 first reached level 2 on the Torino scale to the moment its most dangerous reading was fully retired, the entire episode that would eventually be remembered as the most alarming asteroid scare in modern astronomy lasted less than a week, a strange kind of whiplash for the handful of people who had spent that same week bracing themselves for a much longer fight. It is worth sitting for a moment with how strange that timing actually is. The single most alarming asteroid risk assessment in the history of the Torino scale, and the data that quietly ended it, existed within 150 miles of each other for the better part of 3 months, on the very same Arizona mountain, without anyone connecting the two. This was not a failure of anyone's diligence. Nobody had any reason to go looking through Spacewatch's March archive for an object that would not officially exist on paper until June. Astronomical archives of this kind hold millions of images, each one taken for its own specific purpose, and there is no practical way to comb through all of them in search of objects nobody yet knows to look for. The connection only became findable once the December crisis gave people a specific reason to look for it, and once that reason existed, the people involved found it within days. It is less a story about a mistake being caught than a story about how much of this work depends on being handed a reason to look somewhere new, and about how often that reason, once it finally arrives, turns out to have been sitting nearby all along, waiting. Even this resolution was not the tidy, permanent ending it might have seemed on the night it arrived. In late January of 2005, astronomers led by Lance Benner, a radar specialist at NASA's Jet Propulsion Laboratory, who would go on to spend much of his career tracking near-Earth objects this same way, obtained the first radar measurements ever taken of Apophis, bouncing a signal directly off its surface rather than simply tracking the sunlight it reflected. Radar works on the same basic principle as an echo bouncing off a canyon wall, except the wall in this case is a moving asteroid millions of miles away, and the returning signal can be timed and measured precisely enough to pin down a distance no telescope alone could match. A telescope can only tell you where an object appears against the background of stars, a measurement that grows less precise the farther away the object sits. Radar, instead, times how long a signal takes to travel out, bounce, and return, and measures how the reflected signal's pitch has shifted along the way, yielding a distance and a velocity far more exact than positional astrometry alone could ever provide. When that radar data came back, it did not quite agree with the orbit computed from the March photographs. The discrepancy was not enormous, but it was real. It shifted Apophis's calculated path roughly twice as close to Earth as the photographic solution alone had suggested. The 2029 impact possibility remained eliminated either way, but the correction was a useful reminder that no single dataset, however dramatic its arrival, was ever going to be the final word on an object this newly discovered. Every method, photographic astrometry, radar ranging, each one built on different physics and different sources of error, had something to contribute, and the true orbit only came into focus by holding all of them up against each other at once. With the immediate danger to 2029 gone, attention shifted to a narrower and more technical question, one that would occupy astronomers for years rather than days. Apophis's 2029 passage past Earth would not leave its orbit unchanged. A planet the size of Earth, past this closely, bends the path of anything moving through its gravity, the same way a marble rolling past a bowling ball does not roll in a straight line. The overwhelming majority of the possible paths through that gravitational bend led somewhere harmless. But astronomers using the Valsecchi circle method, a mathematical technique for mapping exactly which points in space during a close approach, set an object up for a return collision at a specific future date, identified a small, particular patch within the range of Apophis's possible 2029 positions that would do something else entirely. Astronomers call a region like this a keyhole, a target no more than roughly 800 meters wide, sitting within a field of uncertainty that, at the time, still stretched for many thousands of miles. If Apophis's true position during the 2029 flyby happened to fall inside that one small keyhole, Earth's own gravity would bend its path in just such a way as to guarantee a return collision exactly 7 years later on the 13th of April, 2036, Easter Sunday. That year, though nobody involved in the calculations seemed to make much of the coincidence at the time. An 800-meter keyhole sounds small, and it is small, but it is worth understanding what it actually means for something to be a keyhole rather than simply a miss or a hit. Nobody was suggesting Apophis was aimed at that patch of space the way a bullet is aimed at a target. The keyhole was simply one thin slice within an enormous range of still possible positions, no more special to the asteroid's actual physics than any neighboring slice, except for the specific consequence attached to it. Picture the entire range of Apophis's uncertain 2029 position as a target the width of a small American town, and the keyhole itself as a single parking space somewhere inside it. Not impossible to land in, by any means, but a small enough fraction of the whole that the odds of landing there, by chance, absent better information, remained genuinely low from the outset. As more observations arrived over the following months and years, the same process that had already worked once began working again. The range of possible positions kept narrowing, and the fraction of that range occupied by the keyhole kept shrinking along with it, the town-sized target slowly closing in towards something closer to the asteroid's true single position. By August of 2006, the numbers had come in clearly enough that Apophis was lowered all the way to 0 on the Torino scale for the first time since the crisis had begun. The keyhole had not vanished as a mathematical possibility, but the odds of Apophis actually threading it had become small enough that the scale built to communicate exactly this kind of risk no longer considered it worth a non-zero rating at all. Almost nobody outside the small community that had lived through the original Christmas crisis noticed this particular milestone when it arrived. There was no wire service rush this time, no dinner table conversations about a doomsday asteroid resurfacing after a year and a half of quiet. That asymmetry says something true about how these stories actually move through the wider world. The alarming number makes the news, and the patient, unglamorous work of walking that number back down almost never does, even though the second part is by far the more common outcome, and, in its own way, the more remarkable achievement. That should have been close to the end of the story, and for the 2029 and 2036 questions specifically, it very nearly was. But one more thread remained loose, and it involved a force far subtler than gravity, one that rarely gets any attention in ordinary conversations about asteroids and orbits. It is called the Yarkovsky effect, named for the 19th century engineer who first proposed it, and it works something like this. An asteroid tumbling through space absorbs sunlight on whichever face happens to be turned toward the sun, and then, hours later, radiates that same warmth back out into space, as the asteroid's rotation carries the now heated surface around to face away from it. That radiated heat carries away an infinitesimal amount of momentum, and because the warm patch of surface faces away from the sun at a slightly different moment than it faced toward it, the resulting nudge does not cancel out. It pushes, very slightly, in one consistent direction, orbit after orbit, for as long as the asteroid keeps spinning the way it does. The size of that push depends on details that are maddeningly difficult to pin down from Earth. A dark, rough surface absorbs and re-radiates heat differently than a smooth, pale one. A slowly tumbling body distributes its warm and cool patches differently than one spinning cleanly around a single fixed axis. Even the density of the loose material lying across the surface matters, since looser, more insulating rubble holds heat differently than solid, exposed rock. Every one of those properties was, for years, only loosely known for Apophis, which meant the resulting push could only be bracketed within a range of plausible values rather than pinned down to a single number. Astronomers had a name for the mechanism and a rough sense of its scale. What they did not yet have was the one measurement that would have told them with confidence exactly how hard and in which direction it was actually nudging this particular asteroid. A single Yarkovsky nudge is almost too small to imagine. It resembles nothing so much as a savings account that earns a fraction of a cent in interest on any given day, utterly beneath notice in the moment, and yet left alone for long enough, capable of quietly reshaping the entire balance. Over a handful of years, the effect changes an asteroid's orbit by a distance too small to measure. Over decades, spread across tens of thousands of trips around the sun, it can shift that same orbit by a margin measured in miles, which is more than enough to matter when the question at hand is whether a future path threads a keyhole only half a mile wide. Astronomers could estimate roughly how large that push ought to be for an object Apophis's size. What they could not yet do was pin it down to the one precise, confident number that would let them stop treating it as a range of guesses and start treating it as a known, fixed quantity. That uncertainty is precisely what kept a third date on the calendar from being fully closed. Apophis's orbit, nudged by an unmeasured Yarkovsky push over the decades following 2029, could in principle drift toward yet another keyhole, one tied to a possible return collision in 2068. A published risk analysis in 2013 calculated that this later possibility, once the full range of plausible Yarkovsky values was accounted for, exceeded one chance in a million. A small number by any ordinary standard, but large enough on a scale built to flag exactly this kind of long-tail risk, to keep the case technically open decades after the original Christmas crisis had faded from memory. The number did not sit still after that. As additional years of tracking data accumulated and the range of plausible Yarkovsky values slowly narrowed, later estimates refined that same 2068 figure down to somewhere near one chance in 189,000 and refined it again by the start of 2021 to something closer to one chance in 900,000. For a stretch of years in between, the 2068 figure was, by some estimates, quietly higher than the already eliminated 2036 figure had been at its own final measurement. A strange piece of arithmetic that says less about Apophis growing more dangerous over time than about how differently each of these questions had been measured and refined, and how much patience it took to keep narrowing a number that kept a healthy distance from zero without ever fully proving itself safe. The 2036 question, at least, reached its own clean resolution well before that. Radar observations at Goldstone in January of 2013 narrowed Apophis's orbit enough to push the 2036 collision probability below 1 chance in a million, and within a few more months that same year, additional analysis eliminated it as a realistic possibility altogether. 2068 remained the one loose thread, kept alive not by any dramatic new evidence, but by the simple, patient mathematics of an effect too small to measure directly with the instruments then available. What finally closed that last thread was not a cleverer calculation, but more time and better instruments, doing what they do best, accumulating enough observations that a force once too subtle to measure became, eventually, measurable outright. By the last weeks of March in 2021, radio antennas at the Deep Space Network's Goldstone complex in California and the Green Bank Telescope in West Virginia bounced signals off Apophis, while the asteroid sat roughly 10 6/10 million miles from Earth. Close enough for those signals to return detailed enough echoes to refine both its orbit and its physical shape at the same time. This was a different kind of radar work than the ranging measurements taken back in 2005. Rather than simply timing an echo to learn a distance, the 2021 campaign built up something closer to a coarse radar image, bouncing signals off different parts of the asteroid's surface and assembling the returning echoes into a rough picture of its shape and orientation, the same general principle used to let a bat find its way through total darkness, just aimed outward across millions of miles instead of across a cave. Combined with more than a decade and a half of additional optical tracking since the original discovery, those observations finally did something that had eluded every previous campaign. They measured the Yarkovsky effect on Apophis directly, rather than merely bracketing it. Once the actual, measured value replaced the old range of guesses, the uncertainty that had kept 2068 technically open simply had nowhere left to hide. Davide Farnocchia, an astronomer with NASA's Center for Near-Earth Object Studies, put it about as plainly as a scientist ever puts anything. A 2068 impact was no longer within the realm of possibility, and the calculations showed no impact risk from Apophis for at least the next 100 years. On the 26th of March, 2021, Apophis was formally removed from the official risk lists maintained by NASA and the European Space Agency alike, each agency running its own independent monitoring system, and each one reaching the same clean conclusion once the new data came in. Removal from a list like that is not a ceremony or a press conference, so much as a quiet administrative fact. An object simply stops appearing in the next automatically generated report because the computation, run daily like clockwork, on the millions of previous nights, when nothing in particular was wrong, found nothing in particular wrong this time either. 17 years after a soft-spoken engineer in Arizona first noticed an unexpected smudge of light drifting across someone else's photographs, the question of whether this particular asteroid posed any danger to Earth was, at last, completely and permanently closed. 17 years is a long time to spend closing out a single case, and it is worth appreciating what actually filled that stretch. It was not 17 years of alarm. The genuine public alarm, the wire service headlines, and the dinner table conversations lasted a single holiday week in the final days of 2004 and then quietly receded. What filled the 17 years that followed was something far less dramatic and, in its own way, far more impressive. Astronomers returning to the same modest questions again and again, refining a keyhole here, narrowing a probability there, waiting patiently for instruments and observation windows to catch up to a problem that could not simply be solved through cleverness alone, because the missing ingredient was never cleverness. It was time and data and the willingness to keep checking a question most of the world had already stopped thinking about. Closed, that is, as a threat. Not, as it turned out, as a story worth setting aside just yet. By the spring of 2021, Roy Tucker had spent a quarter of a century turning his own backyard observatory into one of the more productive amateur asteroid hunting operations anywhere. David Tholen was still at work in Hawaii on the broader search that had occupied so much of his career, and the object the three of them had first noticed together on an ordinary June night was no longer anyone's emergency. It had become something closer to a settled fact, the kind of entry that sits quietly in a catalogue once its most interesting questions have finally been answered, referenced occasionally in academic papers and specialist newsletters, rarely, if ever, in the evening news that had once found it so irresistible. That, for most discoveries in this field, is as good an ending as anyone gets. Found, tracked, understood, filed, gradually forgotten by everyone outside the small community that keeps the ledger. Apophis was not most discoveries, because here is the piece of this that rarely makes it into the shorthand version. Earth's encounter with Apophis was never going to be a one-way transaction, a bullet that either strikes or misses and is then forgotten. A planet the size of Earth does not brush past a smaller body without leaving a mark on it, even in a pass that never comes close to a collision. The same gravity that would have caused a catastrophe in the version of this story that never happened is still there, still pulling in the version that did. It simply pulls on a body passing safely by, rather than one heading straight in, bending its path the way a river bends around a boulder, rather than smashing into it. And a path that gets bent enough coming in does not necessarily leave along the same kind of path it arrived on. Apophis currently belongs to a family of asteroids called Atens, whose orbits keep them, on average, slightly closer to the Sun than Earth itself, completing one trip around the Sun in a little under a year. The 2029 encounter is close enough, and Earth's gravity strong enough to bend that orbit permanently into a different shape, pushing Apophis into a new family entirely, the Apollo group, whose members spend more of their time farther from the Sun than Earth does. This is not a subtle bookkeeping distinction. It is a genuine physical reshaping of the path a several hundred-meter body has followed since long before humans existed, carried out in the span of a single afternoon by nothing more than the ordinary pull of a planet. Apophis happens to pass unusually close to. The orbit is not the only thing expected to change. Ground-based observations over the years since the original discovery have built up a reasonably detailed picture of what Apophis actually looks like. An elongated body, a little over 1,000 feet along its longest dimension, closer to 340 meters, by the most careful measurements, shaped more like a lopsided potato than a sphere, tumbling through space in a slow, complicated rotation that takes somewhere around 30.5 hours to complete and does not settle into a single simple spin the way a well-thrown football does. That current picture, built up patiently over 2 decades of ordinary telescope time, is itself expected to become outdated the moment the 2029 encounter actually happens. The mechanism behind that expected change is the same one that raises the ocean tides here on Earth, simply scaled down to the size of a single tumbling rock. Earth's gravity does not pull on every part of a nearby object with exactly equal strength. The near side of an approaching body feels a slightly stronger tug than the far side does, because the near side is, if only by a few hundred meters, that much closer to the source of the pull. For an object as small and as oddly shaped as Apophis, tumbling erratically rather than spinning cleanly, that uneven pull acts less like a single push and more like a brief, firm shake, strong enough during the closest hours of the encounter to matter, gone again within a day, as Apophis pulls back out to safer distances. Researchers modeling the physics of the flyby have calculated that this shake, applied to an irregularly shaped, already slow-tumbling body passing this close, is likely to measurably alter that tumble, nudging Apophis into a different rotational rhythm than the one it has held for as long as anyone has been watching it. Some of these same models suggest the shaking could be enough to disturb loose material sitting on the surface, shifting boulders, triggering small landslides down the steeper slopes of its lopsided shape, exposing fresher rock underneath that has not been darkened and weathered by billions of years of direct space exposure, the way the surface layer has. This remains, for now, exactly what careful scientists say it is: a leading hypothesis, built on solid physical modeling, not yet a confirmed observation, because nobody has ever had the chance to watch it happen to an object this size, this closely, before. Nobody framed it that way back in 2004, of course, because back then there was still a real, if narrow, possibility that this would turn out to be a story about a planet failing to see something coming in time. It did not turn out that way, and knowing that now changes how the rest of this story ought to be told. The years that followed the original Christmas scare were not spent waiting anxiously for bad news. They were spent doing something closer to the opposite, slowly, patiently trading a wide, alarming range of uncertainty for an increasingly narrow, boring, reassuring one. One radar campaign and one optical tracking season at a time, until a genuine threat had been converted through nothing more dramatic than careful, repeated measurement into one of the best understood trajectories of any object in the solar system. That, in the end, is the real reason the 2029 flyby still matters so much. 17 years after the danger it once represented was fully retired, it is no longer a question of whether Earth will be safe. It is a question of what, exactly, a close pass like this one actually does to a small world made of rock and rubble, whether its tumble changes the way the models predict, whether its surface looks different afterward than it did before, whether the quiet, patient understanding built up over 2 decades of ordinary observation holds up against the one afternoon that will finally put it to the test. Answering that question properly means being there when it happens, not simply watching from a comfortable distance the way every telescope on Earth has had to do so far. And being there is a considerably harder problem than watching from here ever was. And by the time this particular Arizona mountain and this particular string of letters and numbers reached that 100-year clearance in the spring of 2021, the first steps toward actually being there had already, quietly, begun on schedules and budgets and launch pads far from Kitt Peak, aimed at an appointment still years away, right now. Tonight, Apophis is not visible to you, and it would not be visible even if you stepped outside and searched the darkest, clearest patch of sky you could find, no matter how good your eyes or how patient your search. As of this telling, the asteroid sits roughly 1 8/10 astronomical units from Earth, something in the neighborhood of 165 million miles, drifting through the faint background stars of the constellation Cancer, glowing at a brightness so faint that only large professional telescopes, staring patiently through long exposures, can pick it out from the ordinary starlight around it. There is something almost humbling in that. After everything this story has covered, the discovery, the panic, the 17 years of patient refinement, the final clearance, the object at the center of it all is, on any ordinary night like this one, simply gone from human sight, exactly the way it has been gone from human sight for most of the 4.5 billion years it has existed. It will not stay that way. Its own orbit is already carrying it, patiently and without any awareness of the appointment it is keeping, back toward the one planet in the solar system that happens to be watching for it this closely. While Apophis drifts unseen through Cancer, 2 spacecraft, built by 2 different space agencies on 2 different continents, are already in motion toward a shared appointment with it. Neither one is chasing Apophis out of fear. Both are chasing it because the danger is gone, and the opportunity, strangely, is not. The European effort is called Ramses, short for the Rapid Apophis Mission for Space Safety, and it exists because of a very specific kind of institutional patience. A joint undertaking between the European Space Agency and Japan's Space Agency, led from the European side. Ramses received its full funding commitment at a gathering of European Space Agency member states in late November of 2025, clearing the last major hurdle standing between the mission and an actual launch pad. That approval did not come easily or automatically. Missions of this scale compete for funding against dozens of other proposals at every such gathering, and a mission built specifically around a single, narrow launch window has less room for delay than most. Barely 3 months later, in February of 2026, the European Space Agency signed a formal development contract with the Italian aerospace firm OHB Italia to begin building the spacecraft in earnest, a contract worth on the order of 80 million euros on its own, bringing the mission's total committed value to somewhere near 150 million euros once earlier preparatory work is included. Japan's contribution to Ramses includes the rocket itself, an H-3 launch vehicle, along with solar arrays and a thermal infrared imaging instrument, while a university in Switzerland, the University of Bern, is contributing a dedicated camera system built specifically to track surface changes over the course of the encounter. The spacecraft is also expected to carry 2 small companion satellites, no larger than a few loaves of bread stacked together, one of them named for Paolo Farinella, an Italian scientist remembered for his contributions to understanding how asteroids evolve over time. The other envisioned as a possible short-lived lander, a proposal still being refined as the mission moves from paper into hardware. Small companion craft, like these, have become an increasingly common feature of asteroid missions in recent years, riding along on a larger spacecraft the way a lifeboat rides along on an ocean liner, ready to be released for a closer, riskier look that the main spacecraft itself cannot safely attempt. Gathering data from angles and distances, the larger, more valuable mothership would never risk on its own. Current planning calls for Ramses to launch in April of 2028 and to reach Apophis by February of 2029, arriving roughly 2 months ahead of the asteroid's encounter with Earth. That timing is deliberate, and it is the entire point of building a rapid response mission in the first place. Ramses is meant to already be sitting there, instruments running, cameras rolling, in the position of a photographer who has arrived at a building early enough to take careful pictures of every wall and window before anyone else shows up to renovate it. The lineage behind Ramses matters as much as its instruments do. Much of its underlying spacecraft design borrows directly from Hera, a European mission already built and flown to study the aftermath of a different, deliberate experiment. NASA's controlled collision with a small asteroid moon called Dimorphos, part of an earlier joint test of humanity's ability to nudge a dangerous object off course, using nothing more than the simple physics of impact. That earlier mission answered a narrow, practical question: can a spacecraft, struck hard enough in the right place, measurably change an asteroid's path? And answered it successfully. Ramses takes that same proven hardware and points it at an entirely different kind of question, aimed not at an object anyone needs to nudge, but at one that a much larger, entirely natural gravitational nudge is about to reshape on its own, whether anyone is watching or not. Because that, at its core, is the scientific opportunity driving all of this. Researchers expect the 2029 encounter to measurably reshape Apophis, its spin, quite possibly its surface, and the only way to know for certain what changed is to have detailed, trustworthy pictures of what the asteroid looked like beforehand. Ground-based telescopes have done remarkable work building up that picture over 2 decades, but they have always been working from millions of miles away, squinting at a point of light rather than examining a place. Ramses, sitting in Apophis's own neighborhood weeks before the encounter, will finally close that gap, gathering the kind of close, detailed, high confidence before record that no telescope on Earth, however large, could ever fully match. America's contribution to this story is a spacecraft with an unusually long resume already behind it. It began its working life as OSIRIS-REx, launched years earlier to travel to a completely different asteroid, a dark carbon-rich body called Bennu, orbit it patiently, and eventually reach out and collect a sample of its surface material to bring home. The Bennu mission alone would have justified the spacecraft's existence. Over nearly 2 years spent studying that asteroid up close, its instruments mapped Bennu's surface in extraordinary detail. Discovered, the asteroid was venting small particles of its own material into space, in a way nobody had fully anticipated, and eventually reached down to briefly touch its surface, firing a burst of nitrogen gas to stir up loose material and capture a sample before backing safely away. That sample capsule parachuted down over the Utah desert on the 24th of September, 2023, closing out one of the more successful sample return missions NASA has ever flown, and delivering scientists more than enough material to study for decades to come. But the spacecraft that had carried that sample home was not finished. It still had roughly a quarter of its original fuel supply remaining and a full suite of working instruments, essentially the same cameras, spectrometers, and laser ranging equipment that had spent nearly 2 years patiently mapping Bennu from every angle. Rather than let a capable, functioning spacecraft drift into a purposeless orbit around the Sun for the rest of its operational life, NASA's engineers realized its existing trajectory could, with modest adjustments, to be redirected toward exactly the encounter this story has been building toward all along. The spacecraft kept flying, only the mission and the name changed. It became OSIRIS-APEX, the word Apex standing in for Apophis Explorer, a spacecraft built for one asteroid quietly repurposed, fuel and all, for a second one nobody had originally planned for it to visit. That repurposing carries a scientific bonus most casual observers overlook. Bennu, the spacecraft's original destination, belongs to a dark, carbon-rich family of asteroids, its surface material closer in composition to ancient, unheated organic sediment than to ordinary rock. Apophis belongs to an entirely different family, one dominated by silicate minerals and metallic iron and nickel, closer in makeup to the rocky, metal-bearing debris that built the inner planets in the first place. A single spacecraft, carrying a single set of instruments, calibrated once at Bennu and now aimed at Apophis, will end up having examined two chemically distinct kinds of asteroid up close using an identical toolkit, a natural experiment in comparison that no mission planner could have designed from scratch, and that only happened because a spacecraft with fuel to spare found itself with somewhere useful left to go. Scientists studying either family of asteroid, stony, or carbon-rich rarely get the luxury of comparing results gathered by two different instruments built years apart by two different teams. Here, for once, the same eyes will have looked closely at both. There is also something worth noticing in who ends up doing that work and how little it resembles the story most people would expect. This was never a tale of a single genius spotting danger and a single hero racing to avert it. It was Roy Tucker, testing equipment on an ordinary night, finding something he was not looking for. It was David Tholen, bringing more than a decade of quiet expertise to bear on a threat that turned out not to be one. It was Fabrizio Bernardi, present at the discovery and rarely mentioned since, doing the same careful work as his better-known colleagues. It was Gordon Gerard, recovering a lost object from the other side of the planet without knowing what he had found. It was Anne Descour and Ariana Gleason, searching an old photographic archive because a crisis finally gave them a reason to look. It was two automated systems on two continents, cross-checking each other without either one knowing the other existed until the results came back nearly identical. It was Lance Benner, bouncing radar off a rock millions of miles away to catch an error nobody else could have found. And now it is engineers in Italy, Japan, Switzerland, and Arizona building hardware for an encounter that will not hurt anyone, simply because the chance to understand it properly will not come twice. No single one of these people would call themselves the protagonist of this story. Collectively, they are the entire reason it has an ending worth telling at all. Because that, ultimately, is what the 2029 encounter actually represents. Once the fear has been stripped away and only the opportunity remains. Apophis was never going to be humanity's only close call. It was simply the first one large enough and well-timed enough and lucky enough in its own orbital geometry to be caught decades in advance rather than days in advance, giving two space agencies the rarest possible gift in this line of work: enough advance notice to actually prepare a proper welcome rather than a hurried, improvised response. Most near-Earth objects large enough to matter and small enough to have gone unnoticed until recently will not offer that kind of warning. Some future object found with a fraction of the lead time Apophis provided may someday put every lesson learned from Ramses and Osiris Apex to a use nobody wants to need. The patient, unglamorous, decades-long work this story has followed: the discovery, the false alarm, the 17 years of careful refinement. The spacecraft, now converging from two directions on an asteroid that no longer threatens anyone, is not really a story about one object after all. It is a rehearsal, conducted for real on the one asteroid considerate enough to give humanity the time to hold it. Somewhere out there tonight, invisible even to careful eyes, is a lopsided, tumbling piece of rock that has been circling the sun since before there was anyone around to name it, notice it, or worry about it. In under 3 years, for a few hours, it will finally meet the planet it has spent 4.5 billion years quietly passing near, and for the first time in its entire existence, someone will be watching closely enough and prepared thoroughly enough to see exactly what that meeting does to it. Nothing about that encounter will save a single life or avert a single tragedy, because there was never a tragedy here to avert in the first place. What it will do, if the two spacecraft now converging on it managed to keep their long-planned appointment is turn 1. Very old rocks, very ordinary journey around the sun into the clearest lesson anyone has ever had in what a close call with a planet actually looks like from the inside. While it is still happening, that is not a small thing to have earned from an asteroid that, on the night it was first noticed, looked like nothing more than an unremarkable smudge of light in someone else's photographs. It took a soft-spoken engineer testing equipment he had no reason to think would matter, a colleague who had already spent his career preparing for exactly this kind of moment, a third astronomer whose name rarely makes the retelling, an archive. Nobody had reason to search until they suddenly did, and 17 years of quiet, unglamorous, well-funded patience before anyone could say, with real confidence, that watching this particular encounter unfold would be a privilege rather than a catastrophe. Most of that work will never be remembered by anyone outside the small community that carried it out. None of it needed to be dramatic to matter. It only needed to be careful, and it was for exactly as long as it took. Sleep now, the sky keeps its quiet appointments, and tonight, so can you.